Hello, I'm going to start doing some video lecture summaries so that you can have something to look at to review after class and between office hours, before exams, those sorts of things. So we're going to start with a review of the things from last semester that we should know about how to prepare carbonyls. So one of the first things, probably one of my favorite reactions from the first semester is ozonolysis. In ozonolysis, what we do is we take an alkene like this, for example, treat it with ozone, followed by some sort of a reduction with either zinc or dimethyl sulfide. And what this will give us is as if we cleaved the alkene right down the middle, and where it was cleaved, both sides of that alkene basically had an oxygen put in there. So in total, this would create also two of this, because we have even carbon chains on both sides of the alkene. So this carbon chain is retained, and we have two of them. In total, this is a 4-electron reduction, or 4-electron oxidation, excuse me, because we're starting from alkene carbons with hydrogens here. So this carbon is 0, 0, 0, minus 1, 0, 0, 0, minus 1. To over here, we have two of these, but this is 0, plus 1, plus 1, minus 1, so this is a total of a plus 1, but 2 plus 1s is obviously plus 2, so we've gone from minus 2 to plus 2. It's a 4-electron oxidation. Okay, so mechanistically, I'm just going to start with a pretty simple alkene, so it's easier to draw throughout the mechanism. But here we have the structure of ozone. Okay. So this minus charge on this oxygen is going to push electrons to the one side of the alkene, which forces those pi electrons to come to this oxygen, and finally there. This will create a neutral intermediate, but that triple oxygen is pretty unstable, so that's going to fall apart. First of all, just to specify, this is a 4 plus 2 cycle addition. And then we do a retro 4 plus 2 here. And the air pushing for that, like this, and like this, and like this. Okay. Which breaks that bond, sorry. Still have there's an H on it. So that's one side of it. This other side split off here. Makes formaldehyde. Okay. But we're not actually done once we get to that point, because these will further react. We can line up, remember, this will have a partial positive charge down here on the carbon, partial negative on the oxygen, so this negative charge is going to want to be facing down. That's more like it. So this can now attack the partial positive here, and then this pi bond will be able to jump over to that alkene. I mean, it's not really far over because this is more likely on this side, but that carbon. We now have that methyl there. This oxygen connected to that carbon. Okay. We have another neutral intermediate. And then the rest of the mechanism isn't relevant to much also what we'll do in this class. But we'll be using sulfur, dimethyl sulfide, as a reducing agent. And we'll get our products. I don't know if this is still, yep. Those are our products. Hi, as I'm adding that, I realized that the products I wrote at the bottom were incorrect. This is what it should look like. I just forgot to put the H's on the formaldehyde. Then as a byproduct, DMSO, dimethyl sulfoxide. So ozonolysis can also be done for rings. I just wanted to add this one in here. So say we have a 5-membered ring, and we treat it with ozone, and then at the end reduce it with zinc. What we're gonna do is open this ring along that bond. So we'll have a total carbon chain of this number of carbons. We'll have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. On the second carbon, we'll have our ketone, and on 3, 4, 5, 6 carbon, we'll have our aldehyde. That H there is coming from this H. Next, we'll look at alkyne hydration. So alkyne hydration, we're first going to look at a terminal alkyne, and we're going to want to do Markovnikov hydration. So we're going to want to hydrate, focusing on this more substituted carbon. Okay. So we are going to do that with catalytic mercury and hydronium and water. Okay. And this will just get us acetone. Okay, started with 3 carbons. This isn't triple bond with the H, just want to make that clear. Okay, so this is 1, 2, 3 carbons and an H. Another H is. But yeah, anyways, so how does this one work? Skipping the non-relevant chemistry for this course, we're going to go straight to the point where the alcohol is on. Okay, and from here, we're going to do tautomerization. Okay, and this is under acidic conditions, which is important to know. So first, I'm going to start by protonating the alkene here. Okay, and then once you protonate that, you'll notice that you have a plus charge on that carbon. So how are we going to compensate for that? We are going to use the pi electrons from up here, push down, and we create this. Okay. Now this is an all-octet structure. This is stable, and it's really important in order to. We're going to see this a ton. You can also could have drawn this step already, showing the arrow pushing from up there and kind of doing a concerted movement of electrons, but this works to show why it's happening. So then with water, you can deprotonate. We also regenerate the catalyst, which is the hydronium here. So the more substituted carbon ended with the oxygen, but notice compared to alkene hydrations, we're ending with a ketone instead of an alcohol. And this down here we call tautomerization. Simple way to think about it, or like an acronym, not really an acronym, just the way I think about it, the steps is to protonate, resonate, deprotonate, if it's in acidic conditions. If it's in basic conditions, deprotonate, resonate, protonate. So we're just in the direction. So that's Markovnikov alkyne hydration. We then also have anti-Markovnikov. Okay, so next we're going to look at anti-Markovnikov alkyne hydration, and we can do that using this reagent, which is dicyclohexylborane. So it's basically borane, but 2 of the H's are replaced with cyclohexane rings. Okay, this is a 2-step reaction. The second step is oxidation with hydrogen peroxide and base, like potassium hydroxide here. How does this work though? So first, remember boron has an empty p orbital in a compound like borane, right? So take borane, what are we drawing? It has this empty p orbital, which electrons can move into, and as it does that, it kind of donates a hydride. Okay. So, move this, push those electrons to the boron, and then push that hydrogen back there, and you end up with an intermediate, which I'll draw down here. Okay, that's still visible. Move this down a little bit. Ooh. I'm propping my phone up on one of the university cameras. It's a little uneven too. Okay. Cool. What are we looking at? So this H here that we added is this one, and this H is this one. Just to kind of make sure you're keeping everything in perspective. Okay. Next, oxidizing with hydrogen peroxide, we get to an enol. So basically what the hydrogen peroxide does, if you're just thinking of beginning and end products, replaces this BCY2 group with just an OH group. Okay. Now what we're doing is tautomerizing. But we're going to tautomerize now in basic conditions. So you can see the other one. Because we're in KOH. So just use whatever based on the reagents you have. So that would deprotonate that H, the most acidic proton. Okay. And then we get, might not have enough room. Let's see over here. Yeah. O minus. And then we could draw a resonance structure of this where we put the minus charge on this carbon. Okay. And with this water we made, if you think about this stoichiometrically, we're going to end up using that to deprotonate to get back to equilibrium. Okay. And that's the mechanism for that. We just have some more details to clear up about alkyne hydration in general. So this is number 3. Ooh, the last one was supposed to be 3. So this is 4. They're in no particular order, doesn't matter. Internal alkynes. So again, this one here is symmetrical, which is making this example easier so we don't have to consider extra products. But with an internal alkyne, you can use, again, either pathway. So with our mercury catalyst pathway, we will get this. And the same goes for our other pathway. But what I'm going to use here is another reagent that I think is fun, which is called 9-BBN. Okay. So instead of the cyclohexyl groups, it has this bigger, bulkier group at the back, which I think is fun. And you're getting oxidize that at the end. Okay, so this is an OR, specify this is an all for one reagent. And you get the same product. So you can use either pathway for those cases. All right, the last reaction that I want to cover for sort of review of Orgo 1 is Friedel-Crafts acylation. This is really pedagogically important reaction, I think, to learn and talk about now before getting into a bulk of the semester, because there's some things like the acylium ion intermediate that we need to look at a little bit more in depth. So this is an aromatic, electrophilic aromatic substitution reaction. In this example, I'm going to use benzene. We're going to add the benzene with an acid chloride, and this is going to create this. Now, how do we get there? So we're first going to look at just the reagents and do some chemistry with those. This chlorine can give electrons to aluminum. Remember, aluminum also has an MTP. It's in the same column as boron group. Sometimes it's the simpler chemistry that's still the namings. Yeah. Okay. This has a minus charge and this has a plus charge. So what we can actually do now is kick out this group, kick out an AlCO4, because that's a good enough leaving group, and we create, oops, I'm working on myself. Down here I'll draw it. An acylium ion, okay, as well as AlCO4, which is in equilibrium with AlCO3 and chloride. Okay, this acylium ion, it's all octet, and it's good enough for me. So what we're going to do now is use, this is benzene, so benzene doesn't really have 3 pi bonds like this. This isn't the true structure of benzene, but we'll still use the equivalent of 2 electrons of the electron density to attack the carbon on this acylium ion, the one that's triple bonded to the oxygen, and open that up. And I attacked it on this side, but I'm going to draw it on this side. All right. Now, really close to the end product, all we need to do is deprotonate here and do something elimination-like. And you're like, wait, how can we do an elimination with chloride? That's not a good base. It's because of this carbocation here, and it favors the aromaticity. So, there we go. So that's all I'm going to cover in this video. Stay tuned to the next video where we talk about the oxidation of alcohols.